5.3, Force and Motion in Two Dimensions. This is the last section in Chapter 5. So we are going to have a test on Chapters 4 and Chapters 5. It's coming up pretty shortly. I'll let you know in class when that will be, but this is the last section in Chapter 5. And we are dealing with motion and force in two directions. Now we've kind of already touched on this a little bit in class when we did the lumberjack problem, or not the lumberjack problem, I guess we could call it the lumberjack, or the problem in which someone was lifting the sign at a certain force at 15 degrees, someone else was lifting the sign at 105 degrees at a certain force. What's the cumulative force and direction of both of those? We've kind of covered that. Where we have to talk today is forces on inclined planes and kind of what is the result there. But before we do that, I just want to revisit equilibrium. I feel like every time in this section so far I've hammered home the fact that if you have no acceleration, your net force is 0. So if you have no acceleration, your net force is 0, just to kind of talk about that. Now, what it's going to ask you to do is it's going to solve for your equilibrium. Well, what is your equivalent? It's essentially a force that counteracts the force that you just solved for. What do I mean by that? Well, let's say when we did the lumberjack problem, where they were lifting the tree or the sign, we figured out that they were lifting it at 13 newtons at 77 degrees. Well, what force is going to counteract 13 newtons at 77 degrees? Well, it's going to be 13 newtons in the exact opposite direction. So we're going to add 180 to that, and it would be 13 newtons at 257 degrees. All right. So it'd be 13 newtons at 100 or 257 degrees. If I had a force going up at 100 at 90 degrees, what would my equivalent be? It would be 100 newtons at 270 degrees. All right, since it's a full 190 turn. So you're going to be put in positions where you're going to have to find two forces, and then it's going to ask you to solve the equilibrium. All right, the equilibrium force. And that's the forces is the same amount of force, it's just in the exact opposite direction. So that is the equilibrium force. So that is the first thing. And if you have questions on class, we can talk about the equilibrium force, or you can look at page 131 in your book, but both of them are going to kind of cover how it works. But what I just talked about, it's the same exact force, 180 degree change in the angle is your equilibrium force. All right. Now, what is our big focus on section 5.3 is forces and how forces are on inclined planes. Because if you think about it, when you have a force on an inclined plane, let's say I have a box on a hill. All right. Gravity goes down, but is that going to be measured perfectly, considering the fact that we have an angle? Because technically the normal force is pushing down, or we have a force like this and we have the hill pushing up at a normal force. So we have gravity to consider. We also, the box is really staying on the hill because the force of friction is holding it there. If we move it down the hill, that will be our force of motion. Right? Or up the hill, vice versa, whichever direction you're going. So we have a couple equations to take into the force of weight that kind of handles this part of the matter and this part, because we're dealing with an angle. So we have the perpendicular force, right? Perpendicular force, which would be right here. Let me do that in a color other than red. The perpendicular force right here is equal to the force of weight times the cosine of theta. Then likewise, we have the parallel force, which is equal to, and this would be the parallel force, the force of friction could equal the parallel force in this example, the force of weight times the sine of theta. Now how do we figure out force of weight? Force of weight is really the force of gravity, so force of weight is really simply mass times gravity. Now, it will give you, sometimes it'll give you the weight of the object already in newtons, and therefore it's already calculated in the force of gravity. So you have to kind of be aware of that. If it gives you 25 kilograms, you're going to have to factor in gravity. But if it says the box weighs 600 newtons, the force of weight's already been calculated. So keep in mind that you can give weight in newtons. So just be alert of that. So we have the perpendicular force is equal to the force of weight times the cosine of theta. The parallel force is equal to the force of weight times the sine of theta. And then when we solve for acceleration is g times the sine of theta. So those are kind of our last three equations in chapter 5. Well, let's look at an example on how we would do an example with this. A crate weighing 562 pounds. So again, what I just talked about on the last slide, it's already factored in weight. Our force of W is 562 pounds. So we have our force of W is 562. Is resting on a plane inclined 30 degrees. So theta is 30 degrees above the horizontal. Find the components of the weight forces that are parallel and perpendicular. Now this one's fair enough. They're just asking us for what are the parallel and perpendicular forces. Well, perpendicular force, remember, is equal to the perpendicular force is equal to the force of weight times the cosine of theta. Well, that's equal to, well, the force of weight we already determined was 562 times the cosine of theta. The theta is 30. Go ahead and plug that in. 562 times the cosine of theta. And we end up getting 487 newtons as our perpendicular force. Now likewise, it asks us to solve for also the parallel force. Well, the parallel force is equal to the force of weight times the cosine of theta. That is equal to the force of weight we know is 562. Sorry, not the cosine. Sorry, should be the sine. My bad. Should be the sine of theta. So the force of weight times the sine of theta, the sine is 30 degrees. 562 times the sine of 30 degrees, that ends up being 281 newtons. Now, again, sig figs, don't worry as much about sig figs, because technically the 30 degrees here, we should have 500 and 300 if we're going to do sig figs. But those are plugging in the equation. So that's just kind of a simple application of the equation. Now, what happens when we take a problem and we want to solve for more than just the force at play? We have our net force in play, and maybe we want to solve for velocity. What you can do is you can take all the factors that we've solved for chapters 2 through 5, and I can take a force problem and use the equations from chapters 4 and chapters 5, and then solve for velocity using the equations from chapter 2 and chapter 3 via acceleration, because in all 4 chapters we've talked about acceleration. So if we take a look here at the question, a 62 kilogram person on skis is going downhill sloped at 37 degrees. The coefficient of friction between the skis and the snow is 0.15. How fast is the skier going after 5 seconds after starting from rest? Well, they're starting from rest and they are moving downhill at some type of velocity. They're going to have acceleration. So we know we are going to have acceleration moving down the hill. Before I even start plugging in numbers or doing anything like that, what I want to do is I want to draw a picture. So we have our hill, we have our skier. Better give him arms. He's going downhill. Now we have a multitude of forces happening on our skier right now. Right? We have the perpendicular force. We have the force of friction, which is also going to act as the force of friction. That's also going to act as the parallel force. We have the force of the skier going downhill. And we also have the normal force pushing up on the skier. So we have a bunch of forces at play here. Now, the skier is not sinking into the hill at all. So really, I should have my normal force and my perpendicular force should be the same. So remember that. My normal force is equal to my perpendicular force. And I've also already established that the force of friction is equal to the parallel force. So if we are going to go ahead and do an equation, we would have the net force is equal to the force of the motion of the skier shoot. Let's go back here a second and erase this force of friction here and our force of motion. Let's kind of rephrase that. The force of friction is resisting our skier. The parallel force is the force that is actually the force of our motion. I kind of explained that wrong. So to go back, the normal force and the perpendicular force are the same. They are equal to one another. However, since our skier is going downhill, the normal force, our normal force here, is greater than the force of friction. So we want to solve for, if we look at the question again, a 62 kilogram person is on skis going downhill 37 degrees. Information. The coefficient of friction between the skis and the snow is 0.15. Information. How fast is the skier going after 5 seconds? Well, we need VF, but there is nothing that can give us VF directly in this problem. However, as I said before, what's our link between chapters 2 and 3 and 4 and 5? Our link is acceleration. So we want to solve for acceleration. Well, how are we going to do that? Well, the net force in this problem, if we look at the picture I just drew, our normal force and our perpendicular force are equal. What is different is our force of friction is small and our motion, since we're going downhill, is quite large. So our net force is equal to our parallel force minus the force of friction. Now, net force is equal to m times a. The parallel force is equal to the force of weight, right, times the sine of theta, right, minus the force of friction is equal to the coefficient of friction times the normal force. However, we concluded that the normal force is equal to the perpendicular force. So now we're going to go mass times acceleration is equal to the force of weight times the sine of theta minus the coefficient of friction times the perpendicular force. And we know the perpendicular force is mass, or the force of weight. We know that the perpendicular force is equal to the normal force, and the perpendicular force is the force of weight times the cosine of theta. Now, we need to figure out the force of weight. Well, we know the skier is 62 kilograms. All right, force of weight is mass times gravity. Well, 62 times 9.8 is 607.6. So let's go ahead and let's put everything in the numbers that we know. All right, our mass is 62 times our acceleration is equal to our force of weight is 607.6 times the sine of theta, 37 degrees, minus the coefficient of friction, which is 0.15, times the force of weight, 607.6, times the cosine of 37 degrees. All right. We break that down when we end up doing all this math into the calculator. We end up getting 62 times A is equal to 292. We divide by 62, and our acceleration ends up being 4.7 meters per second squared. Now, we go all the way back up. Everything's in 2 sig figs. Our answer has to be in 2 sig figs. But, more importantly, we're not done yet. We have to do acceleration, or we just solve for acceleration. We want, all right, the final velocity. Well, let's go look on that note card. What do we have for final velocity equations? All right, with acceleration and time. Because we have our acceleration here, and we know our time took 5 seconds. Well, this is pretty easy considering that VF is equal to VI plus a change in t. We're solving for VF. We started from rest, so we're going to take 4.7 times 5.0, and when we do that, our final velocity ends up being 24 meters per second with sig figs considered. All right. So it took a while to get there, but what's important is you can link equations from Chapter 2 and 3 to equations of Chapter 4 and 5 using velocity. So what works is if you draw yourself a picture, that picture is key to kind of helping guide you with what forces are at play. So you'll have a worksheet on Tuesday dealing with perpendicular and parallel forces. We'll review on Wednesday, Thursday, and you guys can expect a test the following Monday. So that's kind of what's up with Chapter 5. Other than that, I hope you guys enjoy homecoming weekend. Have a great weekend if you're watching this on the weekend, and we'll see you on Tuesday.